All right, so we're going to talk about power today. I'm going to talk through kind of what power is, and then we'll get to the equation. So you don't have to necessarily worry about getting those down right this second. But power is a new concept for us. It has a couple different equations that goes with it that both have to do with work and energy. Okay, so we're going to be able to do some substitutions, see a couple different versions of our equations here. But power is essentially the rate at which work is done. Okay, so it's a rate. Work over time, right? Anytime we look at a rate, it's whatever we're trying to find divided by how much time it took. Okay, so velocity is a rate of distance over time, whereas power is the rate of how much work is done per time unit. Okay, so it's the rate at which work is done, which means your equation for power, your really original equation for power is work divided by time. Okay, we can also think of this as work being energy transformed divided by time, because when something is doing work, it's essentially transforming energy, whether it's a transformation from kinetic to potential or back and forth, whether it's transforming into thermal energy, which we don't talk much about in this chapter, but essentially it's a transformation of work or of energy. Okay, so there's a couple different ways we can solve for power. But the unit for power is the watt. Where do we see that watt unit at pretty commonly? In light bulbs, right? So that's the amount of power that's being output is usually in watts. Okay? A watt is equal to 1 joule per second. Okay, and that comes from work being in joules or energy being in joules divided by time. So that means your time unit always needs to be in what? Seconds. Always needs to be in seconds. Okay, so when we solve for power, our time has to be converted to seconds. Power is also measured in horsepower if we use larger quantities of it. Okay, and where do we see horsepower at? In cars or in engines. Okay. So the conversion factor between watts and horsepower is 1 horsepower is equal to 746 watts. Okay, so that's a conversion factor that you might want to have down. We need to remember that power and energy are not the same thing. Okay, power is a rate, and energy is the amount of substance that's being output. Okay, so power is the rate at which it's being changed or transformed. Energy is just the total amount of energy that we're looking at a certain interval. Okay, so when we're talking about a person and their power output or their energy output, a person's work, the ability that they have to do work is limited. Okay, the amount of power that they could output is limited. Can we think about some ways that our work ability is limited?
There are certain things that we can't push or lift.
Okay, so there's certain things that we don't have the strength to do. Okay, what about specifically power? How does that get limited? Some things we just can't do that fast, right? There's a limit to the amount of time it's going to take us, okay? Or there's a kind of a window as to how much time it's going to take us to achieve a certain goal, okay? So energy expended is a way that our work is limited. Our body runs out of energy at some point. We're not Energizer bunnies, right? We can't keep going and going and going. Eventually, we've run out of energy. So our body is not transforming that energy fast enough for us, okay? So we've got a limitation by the energy, and we've also got a limitation by the time it takes us to do it, okay? So we can't perform every task at lightning speed, right? We have certain limitations. Our bodily functions have certain limitations as to how fast we can accomplish a goal, okay? So let's think about this example here. You don't have to necessarily write this down, but I want you to think through what's happening here, okay? So if I sprint up 2 flights of stairs, it's going to take me less time, but it takes a lot more energy from my body than if I would just walk those 2 flights of stairs, right? So is my power output increasing or decreasing? Do I output more power when I sprint up the stairs or when I walk up the stairs? When I sprint, because it takes me less time, which means my denominator is decreasing, so my total power would be increasing. Okay, it's going to take the same amount of energy for me to walk that distance up the stairs because the vertical height is the same, right? And energy I'm transforming there goes from kinetic to potential. It's all potential by the time I reach the top of the stairs. Does that make sense? Okay, so by the time I climb to the top of the stairs, I've reached a point where I'm only potential energy anymore. Okay, I could do a lot more work if I climbed higher and I walked at a slower rate. Okay, so if I wanted to look at the amount of work I wanted to do, I could do a lot more if I just walked a farther distance, walked a farther flight of stairs, but I did it at a slower rate. But our bodies have a limitation to how fast we can convert that energy into expendable energy. Okay, so we've got a limitation there. We can't sprint upstairs all day long. There's a limitation that our body has. So that's kind of what I'm thinking here when we're looking in terms of power and energy. What's the difference between those two? Okay, we could expend a lot more energy at a slower rate, or we could expend a lot more power by moving at a faster rate. So there's differences in that. Okay. Okay. Questions here? All right. A 70-kilogram jogger runs up a flight of stairs in 4 seconds. Vertical height of the stairs is 4.5 meters. What's the jogger's output of power? Okay, so how much power is this person putting out? This is going to be what our lab's about today. Okay, we're gonna run up some stairs and calculate our power output. Okay. Okay. The way that we can solve this. Oh, sorry, I'll give you a couple of seconds to get it finish getting it written down, and then we'll work through it. Okay, so essentially what we're looking at here is the total height of the stairs is 4.5 meters. Okay, so if he starts at the bottom and then he runs up the stairs, okay, once he gets to the top of the stairs and he stops, right, that's when the time stops, that's what we're looking at. We're looking at from the time he starts running to the time he stops running. By the time he gets to the top, what has his energy been transformed from what to what? His energy has gone from what type when he starts at the bottom? Kinetic. And by the time he gets to the top, he has what type of energy? All potential. Okay, so he's got all potential at the top. So the work that he's done in this case is to overcome gravity. He's overcoming that gravity and he's gaining gravitational potential. So when we look at our power equation, which is work over time, or energy transformed over time, we're going to use our equation for potential energy. Because the work he's done during that time has been to overcome gravity and to gain potential energy. So he's had that transformation go from kinetic to potential. So that means we're going to be able to plug in mgy over time. Okay? So this is an equation that we'll use a lot for power. When we're talking about people climbing vertical distances, stuff like that, we can set that equal to power. Okay, so if you want to include that on your equation sheet, you can. You don't have to, but that'll be a way that we solve for it. It's kind of an expansion of that first equation. Okay, but mgy over t means that by the time we reach the top of this stairs or mountain or whatever we've done work to overcome gravity and we've transformed our energy to potential. Okay, so we're going to take his mass times gravity times the height of the stairs over time. All right, 771.75. What's our units for power? Watt. Okay, so do we have over a horsepower or under a horsepower? 1 horsepower here. Over, just barely over. Okay, he's moving at a power output of just over 1 horsepower because horsepower is 746. Okay? So that's his power output. We're going to take it one step further and we want to know what's the energy that was required to perform this task. How much total energy did he need to perform this? Okay? How much energy did he need to perform this task? So this is simpler than what it might seem, okay? We solved essentially potential energy over time, right? We solved, which we considered this to be work. All we need to do is take the potential energy that he acquired by the time he got to the top. That's going to give us our total energy for that time frame, that action, okay? Because by the time he gets to the top, he's transformed all of his kinetic energy at the bottom to all kinetic energy at the top. Or, I'm sorry, all potential energy at the top, okay? So we're going to take his mass times gravity times y, or we could take our last answer and multiply it by 4, either way. And I got somewhere around 3,087. Yeah? And what's our unit for energy then? Joules. Good. Joules. Cliff is a 122-meter vertical climb. Record time of 4 minutes, 25 seconds was achieved by a 65-kilogram man. What's his average power output? Okay? Average power output means we're looking for total energy over total time, or total work over total time. He could have gone faster during one section of it and slower during one section of it. That's fine. But his overall average is what we're looking for here. Okay, so we're going to use that same equation to solve. What do we need to do with our time here? Convert it all to seconds. So we'll take 60 times 4 plus 25. Which gives us 265 seconds. Yeah, good. Yeah, units should be watts, sorry, not joules. I don't know what I was doing. The power output by cars is different because it's work to overcome friction rather than work to overcome gravity. So now we're talking about horizontal rather than vertical. Okay, so the work that these cars are doing is to overcome friction. Okay, cars have limitations by how their engines are built. So they have certain limitations as to how fast they can produce power, okay, or the rate at which they can do work is limited by the type of engine they have, okay? So each car is just a little bit different. Each engine is a little bit different, I should say. When you're driving a car, you have to output the most power when you're accelerating, when you're speeding up, or when you are climbing up a hill, right? Those are two obvious examples of when you're going to have to hit the gas, rather than if you're just coasting. If you want to travel at constant velocity, that's going to take less power output than if you're trying to speed up or if you're trying to make it up a hill, right? If you're coasting down a hill, you can take your foot off the gas. Okay. So here's our equation now. Since we're doing work to overcome friction, we're going to be looking at just kinetic energy here. Okay, so we're still going to take power equals work over time, but the work we're transforming, the energy that we're transforming is purely kinetic energy, not potential. Okay, so when we're talking about power running up something or climbing up something, we'll use gravitational potential energy as our transformation of energy. But when we're talking about cars, we're going to look at horizontal, which means we can look at our kinetic energy transformation over time. Okay, so this is another equation that we'll use pretty often if you want to put that on your equation sheet as well. Okay, so a car accelerates from rest to a velocity of 15 meters per second in 4 seconds. Calculate the power output of the car. We're ignoring a frictional force that slows it down even farther. We're still just looking at the work that's being done, okay, over time to give us power. Sometimes we'll have to take into account kind of an extra frictional force, but not in this case. can we remember what this equation is called? What's this principle called? Work is equal to change in kinetic energy. It's called the something something principle. The work energy principle. Okay, so since it tells us it accelerates from rest, we know that work is equal to 1/2 mv squared minus 0. That's why we can go ahead and just plug that equation in for work. Okay, that's how that goes. Okay, that's how that works out. So to find power, we're going to have 1/2 m times v squared, 15 squared over t. Bless you. Okay, and I get somewhere around 28,125 watts. Yeah? No? Okay, I want you to go ahead and convert that now into horsepower. Since when we're dealing with cars, we want to go ahead and convert that to horsepower most of the time. Okay, so if I want to go from watts to horsepower, I do a little T-chart. I want watts on the bottom, horsepower on top. 1 horsepower is equal to 746 watts. So I'm going to divide that by 746. We should always have a smaller number of horsepower than we have of watts. Okay, so don't multiply. Horsepower should always be smaller. It's a more workable number. Okay, and we got about 37.7 horsepower. Okay. Horsepower is just HP. Sometimes I do capitals, sometimes I don't. I don't know why. Okay, so now we're looking at what it takes to climb at a constant velocity of 80 kilometers per hour. Okay, and to solve this problem, we have to know what our frictional force is. Since it tells us we want to move at constant speed. Okay, so does this diagram ring a bell a little bit? Hopefully, okay. We've got an applied force here that we have to take into consideration to solve this problem. And I want to show you kind of how this works out. Okay, this is a progression of equations that we can use for these types of problems with cars. Okay, we're going to take power is equal to work over time. We also know that work is equal to force times displacement. And what's the equation that looks like this? Displacement over time. Velocity. So I'm going to take that displacement over time and plug in velocity, which means we can solve for power by taking the applied force times the velocity. Okay, applied force times velocity. Okay, so this is a big equation that we can use for power as well. Really, either of these two would be okay to write down, but you probably want definitely the bottom one. Okay. So now we can start kind of looking at our diagram a little bit more clearly, since we know that we have to deal with the forces. Okay, so we want the force that the car is applying to climb at a steady velocity. Okay, so how do we go about solving for that applied force if we want to move at constant velocity? Let's set up our net force equation first. So F net in the x direction, right? We're only looking at x forces. How many forces do we have in the x direction on this diagram? 1, 2, 3. Our parallel force, remember, is our component of our gravitational force. It's pulling it down the incline as well. So frictional force is pulling it down the incline, and parallel force is pulling it down the incline. Applied force has to be enough to overcome both of those. Okay? So to solve for this, we're going to take our F applied minus F parallel minus force of friction. Okay? And if we're moving at constant speed, what should our F net be equal to? 0. Okay? So 0 is going to equal applied force minus parallel. And then what do we know the magnitude of the frictional force is? 700 newtons. Okay? Can we solve for F parallel? Yes, we can. Okay? And we can solve for F parallel by taking 1400 times 9.8. Which gives us 13,720 as the hypotenuse right here, F sub g. So if I want to find force parallel, I'm going to take sine or cosine of 10 degrees. If my 10 degrees goes right here, I want to use sine. Okay, so that's what I got for my parallel force. Do we understand why I took force applied minus both of those forces? Because they're both opposing that applied force. Okay, they're both pulling it down the incline. Okay, Okay, so now we're going to go ahead and plug in that for force parallel, which means 0 equals applied force minus 2382.5 minus 700. And that's going to give us a force applied equal to, what do we have? 3,082.5 newtons. Okay, that's our applied force. So that's the force that the car must apply, must put out in order to travel at a certain velocity. So now to find power, we're going to take power equals 3,082.5 times its velocity. Can we take it times 80? No, we can't. How do we convert kilometers per hour to meters per second? And I got about 22.2 something. 22.2. Okay. So now we can take our force times our velocity and get our power output. $68,553 watts, or somewhere in that range. Okay, I might have rounded on mine. Okay, and then to get to horsepower, I'm going to divide that by 746. We don't have to do that necessarily here, but we can.